Welcome to Module 13, Solving Quadratics by Factoring. Right now, pause the video, find your writing utensil and a piece of paper. You need a spiral-bound notebook for the course. Note-taking is important so that you have access to what you're learning without having to rewatch the videos. Plus, you can use your notes on the quizzes. To solve quadratics by factoring, we're going to talk about how to solve an equation that's already written in factored form. We're going to find the roots of a quadratic equation, and we're going to solve a word problem using a quadratic equation. Right now, turn to a new page and write down that the agenda for Module 13 is to solve quadratics by factoring. You need a new topic, solving a quadratic equation. And I actually don't want you to write what we're going to write for this example. Here's why. We cannot solve a quadratic equation the same way we solve a linear equation. If we were going to teach this the same way that I taught you how to solve a linear equation, you would add 5 to each side to get your like terms together. So far, so good. We have 3x squared plus 4x equals 5. Now, some of you might be saying we should add these together to simplify our like terms. The problem is x squared and x are not like terms. Well, maybe we need to subtract the 4x from each side to get the x squared alone. So now we have 3x squared equals 5 minus 4x. Well, maybe we divide both sides by 3 to get the x squared alone. So it's x squared equals 5 minus 4x over 3. But how do I get rid of the x squared? Well, now I'm supposed to do the square root of both sides. So that gives me x equal to 5 minus 4x over 3 with a square root on it, and I still haven't solved. Because of the fact that I have an x squared and an x, essentially I have two different variables in the same equation. And I can't solve that equation in the same way that I would have solved a linear equation. What we're going to have to use is something we call the zero product property. So I want you to write a new topic, the zero product property. And I want you to write this down. The zero product property tells us that if we have two things being multiplied to make 0, one of those things must be 0. So for example, in example 1, I have 4 and x being multiplied together to make 0. In order to make something be 0, either 4 could be 0 or x could be 0. Well, 4 can't equal 0, so our only solution to that is that x must be 0. And this is a different way of thinking about how to solve one-step equations for you. For a problem like example 2, again, I have two things being multiplied together to make 0. So I could see if both of them are 0. X could be equal to 0 or y could be equal to 0. There are two ways that this would make this equation true. If x were 0, 0 times y would be 0. If y were 0, x times 0 would be 0. We need to be able to use this zero product property to help us solve quadratic equations. New topic, solving an equation written in factored form. To solve a quadratic equation written in factored form, I want you to write down, use the zero product property. So what I want you to notice is I have two things being multiplied together. These are factors. Factors are things that are being multiplied. I have 9 minus y times 5y minus 6 equals 0. Remember, either one or both of these must be equal to 0 for this to be true. So for the two ways to make this equation true are to separate them, 9 minus y equals 0 and 5y minus 6 equals 0. The nice thing is this creates a pretty easy one or two step equation to solve. We're going to subtract 9 from each side. I'm left with negative y equals negative 9. To get the negative away from the y, I divide both sides by negative 1, and so y equals 9. But that's not the only way to make this equation true. If this were 0, sure, that would make it equal to 0. But it would also be 0 if this one were 0. So we need to solve this, add 6 to each side. So we have 5y equals 6, divide both sides by 5, and so y equals 6/5. So now we have two solutions. Y could either be 9 or y could be 6/5 to make this equation equal to 0. You pause the video and try this one on your own. Notice it's already pre-factored. You should have broken this up into two problems. Z minus 5 could be equal to 0, or Z minus 4 could be equal to 0. We're going to add 5 to each side so that Z equals 5. We're going to add 4 to each side so that z equals 4. And so those are my two solutions. If z is 5, the whole thing's going to be 0. If z is 4, the whole thing's going to be 0. Both answers are correct. Now, sometimes we will have more than 2 factors. Here we have 3 factors. 1, 2, 3. Negative 4u could be equal to 0. U minus 1 could be equal to 0. And u minus 9 could be equal to 0. If I divide both sides by negative 4, I can see that if u is equal to 0, because 0 divided by negative 4 is 0, then that's one solution to make this 0. Or if u is equal to 1, or if u is equal to 9. So if you were to write this in your ALEKS box for your solution, you would want to write this as 0, 1, 9 as your solutions. Now this one's just a little bit different. There's still 3 factors, 1, 2, 3. Negative 4 could be equal to 0, u plus 2 could be equal to 0, or negative u plus 5 could be equal to 0. But can a constant be equal to 0 unless it's 0? Can negative 4 equal 0? It cannot. So we throw that one out. Unlike this one where we had a variable, this one does not. You go ahead and solve these two now. You should have subtracted 2 from each side and gotten that u could be negative 2. Subtract 5 from each side and get that negative u equals negative 5. Divide both sides by negative 1, so u equals positive 5. So your solutions are negative 2 or 5. Now, new topic, solving a quadratic equation by factoring. I'm sure you've already guessed that your equations will not always be pre-factored for you. Sometimes you are going to have to factor. You won't have to write any more notes today if you will write these 3 things down. To solve a quadratic equation by factoring, write the equation in standard form, ax squared plus bx plus c equals 0, factor, and use the zero product property to find the solutions. And I'm sorry, by not writing any more notes today, I mean you won't have to write any more words today. You still should be solving the examples in your notebook. So these are definitely not in standard form because they're not equal to 0. So we're going to start by making these equal to 0 by putting them in standard form. So we have y squared plus 15y equals 0. Now to start off factoring, I always want to look for a GCF. Well, y squared and 15y can both factor out a y. So that becomes y times y plus 15 equals 0. There's no need to use the ABC tree because once I factored out the GCF, the y squared went away. I now have my 2 factors, y and y plus 15. So y could be equal to 0, or y plus 15 could be equal to 0, which means I would need to subtract 15 from each side, so y could be negative 15. So your 2 solutions are negative 15 and 0. You pause the video and try this one on your own. Don't forget that it needs to be in standard form before you start. You should have started by subtracting 14w from each side to make this equal to 0. It has to be equal to 0, otherwise we can't use the zero product property. Then you should have looked for a GCF. The GCF is w, so we're going to take a w out. That leaves us with w minus 14 is equal to 0. Now I have my 2 factors. W could be equal to 0, and w minus 14 could be equal to 0. Well, this one's already pre-solved. This one I just need to add 14 to each side, and so w could be 14. So my 2 solutions are 0 and 14. Now, what if we have a trinomial? There is no GCF for x squared, 8x, and 12. There's no way for me to make the x squared go away, so I'm going to have to factor using my ABC tree. All right, so we said there's no GCF. Now we're ready to factor. We're going to multiply a, which is 1, times c. So we're looking for 2 things that multiply to be 12 and add to be 8. Well, 1 times 12 makes 12. 2 times 6 makes 12. There we go. 2 and 6 adds to be 8. This is what we're using to replace b. So this becomes 1x squared plus 2x plus 6x, and then we just bring down the plus 12, and I'm not going to worry about the equals 0 right now. Now I want to factor by grouping, group my first 2 and my last 2 together. The GCF of the first group is x, so this becomes x plus 2. The GCF of the second group is 6, so this becomes x plus 2. These should match, and they do, so this becomes x plus 2 times x plus 6, and this is equal to 0. Now, when we were factoring, we would have stopped there. But now we need to use the zero product property with our factors to find our solutions. So you've done all the hard work. Now it's just creating your two one-step equations. X plus 2 equals 0 and x plus 6 equals 0. We subtract 2 from each side, so x equals negative 2. Subtract 6 from each side, so x equals negative 6. So our solutions are negative 2 and negative 6. You pause the video and try this one on your own. You should have looked for a GCF, and there isn't one. Now we're ready to do the ABC tree. We're looking for two things that multiply to be negative 21 and add to be 4. Should be some combination of 7 and 3 because 7 times 3 is 21 and 7 take away 3 is 4. But the 21 needs to be a negative, which means the 3 needs to be a negative. The larger number needs to be positive to make a positive 4. This is what we replace our b term with. So this becomes y squared minus 3y plus 7y minus 21. Remember, I always put my negative first so that it's not in the middle here, causing me negative issues. Now I'm ready to factor by grouping. The GCF of the first group is y because both terms have a y. We're left with y minus 3. The GCF of the second group is 7 because 7 and 21 are both divisible by 7, and we're left with y minus 3. These match as they should, so it becomes y minus 3 times y plus 7, and before we would have been done. But now we're actually solving. We need solutions to the equation. So we need to go one step further. We make it y minus 3 equals 0 and y plus 7 equals 0. Add 3 to each side, so y is equal to 3. Subtract 7 from each side, so y is equal to negative 7. So my two solutions are negative 7 and 3, and that's what you put in, Alex, for your answer. Now, these won't always start in standard form. We need to make this be equal to 0. So if I have 4v squared plus 9 equals negative 12v, and I want to make this be equal to 0, I just need to add a 12v. And then you want to think about standard form for your order. None of these are like terms, so we're just going to write them next to each other. 4v squared plus 12v plus 9 equals 0. I want the v squared first, then the v, then the constant. Still no GCF. There's nothing that 4, 12, and 9 are all divisible by, so we're ready for our factor tree. 4 times 9 is 36. I'm looking for two numbers that multiply to be 36 and add to be 12. 1 and 36, no. 2 and 18, no. 3 and 12, no. 4 and 9, no. 6 and 6, there we go, because I need to add these to be 12, because b is 12. So now we're going to rewrite this. The 4v squared stays the same. The 12v changes into 6v and 6v, and we bring down the plus 9. Now we're going to factor by grouping. The GCF of the first group is 2v. That leaves me with 2v plus 3. The GCF of the second group is 3. That leaves me with 2v plus 3. These match as we should. I'm left with 2v plus 3 times 2v plus 3. Notice these are exactly the same. We could do it twice if we want to, but it's not really necessary. I'm going to get the same answer for both. So we have 2v plus 3 is equal to 0. Subtract 3 from each side, so 2v equals negative 3. Divide both sides by 2, and v is equal to negative 3 over 2. So sometimes this will happen. You will just have one solution, and then that will be it. You pause the video and try this one on your own. All right, you should have written this as 2w squared minus 9w, and then you should have subtracted 5 from each side to make 0. We're looking for two numbers that multiply to be negative 10 but add to be negative 9. Some version of 1 and 10 should do it. I need one of these to be negative to make it multiply to be a negative, and I need the larger number to be negative. So our magic numbers are negative 10 and 1. So this becomes 2w squared. I like to put the negative first. That makes fewer negative errors. Plus 1w minus 5. I haven't changed anything. I've just replaced negative 9w with negative 10 plus 1w. Now I'm going to factor by grouping. The GCF of the first group, 2 and 10 are both divisible by 2. W squared and w are both divisible by w. I'm left with, I took the 2 out, so I'm left with w minus 5. These two have no GCF, which means the only thing they have in common is 1, so we bring a 1 on the outside, and we're left with w minus 5. These match as they should, so that's w minus 5 and then that leaves me with 2w plus 1. Now remember that's equal to 0. Typically I would be done, but I'm not because I need to solve. So I have w minus 5 is equal to 0 and 2w plus 1 is equal to 0. Add 5 to each side, so w equals 5. Subtract 1 from each side, so 2w equals negative 1. Divide both sides by 2. So you have two solutions, 5 and negative 1/2. Now let's solve a word problem with a quadratic equation. We sometimes might need to solve a problem about a garden or a field or a rectangle. If you see the word rectangle or garden or field, I would draw a picture. I draw this even for myself when I make my own answer keys. And then let's make sure we know which length or width we're talking about. This is my length and this is my width. It says the length of the rectangle is. That's telling me the length is 3 more than, well that's 3 plus. Twice means 2 times, so that's 2 times the width. And then it says we're finding the area. Well, remember, area is length times width. I know the length times the width is 54. Well, I don't want to use length and width because two different variables in an equation is no bueno. So I'm going to replace the length with what I know the length is equal to, kind of like using substitution. 3 plus 2w times w equals 54. This is definitely not standard form, so I need to distribute first. This becomes 3w plus 2w squared equals 54. Still not standard form because it's not equal to 0, so we're going to subtract 54 from each side. And then none of these are like terms, so it doesn't matter what order I put them in, I just need to put them next to each other. So I'm going to put them in standard form. The number with the w squared comes first, then the number with the w, then the constant, and that's equal to 0. All right, so we've done all that just to get our equation. Now we're ready to factor. There is no GCF for 2, 3, and negative 54, and not all of the terms have a w, so I'm ready to jump straight to my factor tree. Negative 54 times 2 is negative 108. I'm looking for two numbers that multiply to be negative 108 and add 3. Goodness. All right, so I just start going up my list. 1 and 108. No way that's going to make 53. 2 and 54. No way that's going to add or subtract to make 3. Let's see if 108 is divisible by 3. So we have 3 and 36. Nope. Let's see if it's divisible by 4. 4 and 27. Nope. 108 is not divisible by 5. Let's see if it's divisible by 6. 6 and 18, getting closer, but no. Let's see if it's divisible by 7. Nope. Let's see if it's divisible by 8. Nope. Let's see if it's divisible by 9. Yep, 9 and 12. And the difference between 9 and 12 is 3. So let's think about which one of these should be negative. The sum should be positive, so I need the smaller number to be negative. So now I have my magic numbers. This is going to be rewritten as 2w squared minus 9w plus 12w minus 54. I'm going to factor by grouping the first group and the second group. The GCF of the first group is w, so that's 2w minus 9. The GCF of the second group, let's see, I think 12 and 54 are both divisible by 6. That leaves me with 2w minus 9. So my factored form is w plus 6 times 2w minus 9 equals 0. I'm going to split those into 2 to use my zero product property. Minus 6 from both sides, so w equals negative 6. Plus 9 to each side, so 2w equals 9. Divide both sides by 2, and so the width is equal to 4.5. I cannot have a width of negative 6, but I could have a width of 4.5, so the width is 4.5. Notice the directions say find the dimensions. The length is 3 plus 2 times the width, so that's 3 plus 2 times 4.5. 2 times 4.5 is 9, and 9 plus 3 is 12. All right, I want you to have all this written down, use it as an example. You try this one, see if you can do it step by step. All right, so what we've got is an area. We've got a length and a width of the rectangle. It says the length of the rectangle is 5 feet less than double the width. Well, double means 2 times, and 5 feet less than means some stuff minus 5. So there's my two expressions. The area is going to be found by multiplying the length times the width, and that has to equal 33. We're going to distribute, so we get 2w squared minus 5w equals 33. And then that's not in standard form, so we're going to subtract 33 from each side. So that's 2w squared minus 5w minus 33 equals 0. If you got stuck and didn't get that far, go ahead and pause the video now. See if you can figure out what your magic numbers are to start factoring. You should be multiplying a times c. 2 times negative 33 is negative 66. And we're looking for two numbers that multiply to be negative 66 and add to be negative 5. 1 and 66, definitely not. 2 and 33, definitely not. 3 and 22, definitely not. Let's try 4. 66 divided by 4, nope. 66 is not divisible by 5. 66 divided by 6 is 11. Ooh, that's interesting. The difference between 6 and 11 is 5. Is there a way to add those to make negative 5? Yes, if we make that negative 11. So my factored form becomes 2w squared. That one stays the same. We're going to replace negative 5w with negative 11w plus 6w and bring down the constant. We're going to factor in two groups. The GCF of the first group is w, so that's 2w minus 11. The GCF of the second group is 3, so that's 2w minus 11 when I divide. These match as they should. So we have 2w minus 11 times w plus 3, and we made that equal to 0 at the beginning so that we could use our zero product property. Now we use our zero product property. Add 11 to both sides, so 2w equals 11. Divide both sides by 2, so the width is 5.5. Subtract 3 from each side. We can't have a negative width, so we're going to throw that one out. So the width is 5.5. The length is 2 times 5.5 minus 5, which is 6. So we have our dimensions there. I know these seem like a lot. Don't be afraid to reach out to your teacher for some additional office hours if you get stuck moving through these problems. And you're done. These will be available on Haiku if you need to rewatch, and will be available on each skill for Module 13 in ALEKS. You should now complete Module 13 practice problems in ALEKS by selecting Continue My Path. Don't forget you can get an explanation and extra help in ALEKS before you reach out to your teacher. And when you're done with both the practice problems and the notes, then you're ready for Quiz 13, which is in your assessments. Have a great day.